In this video, we're going to learn a special factoring strategy that occurs when our A and C values are equal to perfect square values. So the strategy that we're going to be discussing in this video talks about a strategy that can only be used when A and C are perfect squares. So what we're going to do for the 6 situations below is we're going to decide for which of these A and C are perfect squares. So if I look here at this first example, we have an A value that's equal to 4 and a C value that is equal to 25. Both 4 and 25 are perfect squares because they can be perfectly square rooted to produce an integer. And as a result, this strategy would work on this particular expression. Then from here, if we look at the next one, we have an A value that is 9 and a C value that is 1. Again, because both of those can be perfectly square rooted, this will work with the strategy that we're discussing in this video. This next one down here, we have A is equal to 2 and we have C is equal to 9. Well, 9 is in fact a perfect square and can be square rooted easily, but the square root of 2 is a decimal. It's about 1.41 and then it keeps going. Because of that, A is not a perfect square, and as a result, this strategy will not work for that particular expression. Then over here, we have an A value that's equal to 1, which is a perfect square, and a C value that's equal to 10. And if I try to square root 10 perfectly, I end up with a decimal value of about 3 point something. And as a result, because this is not going to produce an integer when it's square rooted, this entire thing cannot use the strategy we're about to discuss. Then here we have an A value equal to 49. Notice that there's no B value in here. Our B value would really be 0. And our C value is equal to 64. Well, both of those can be perfectly square rooted, and as a result, this strategy will work here. And then finally, we have A equals 2, C equals 1. C equals 1 is a perfect square, but A equals 2 is not. So this strategy would not work for that trinomial. So that's the first step, is being able to identify whether or not the strategy we're about to look at truly does work. So what we're going to do now is we're going to look at these expressions that have A values and C values that are perfect squares, and we're going to look for patterns that we could potentially use to factor a little bit quicker. So to start this problem, I'm going to look at A, and A I can see is 4. And what I'm going to do is with that first term, I'm going to square root the entire first term. So the entire first term square rooted, square root of 4 is 2. The square root of x squared is x. And then if I do the same thing over here with 25, if I square root 25, I find 5. Now that might seem a little bit random at first, but we'll see down the road why these values are important. So what we're going to do now is we're going to forget about the perfect square bit for a little bit, and we're going to just use our factoring trinomial strategy that uses the A, B, and C values to factor this and see if any patterns emerge. So here I can see that my A value is 4, my B value is 20, and my C value is 25. And I need two numbers that multiply to A times C. 4 times 25 is 100. And that add to B, which is 20. And if I start thinking about the numbers that multiply to 100, I discover that 10 times 10 is 100, while 10 plus 10 is 20. So then I can go here to my 20x, and I can split it into 10x plus 10x, leaving the 25 at the end and the 4x squared at the beginning unchanged. And so now if I use my factoring trinomial strategy, I'm going to look for a greatest common factor between 4x squared and 10x. And when I look at those numbers, their greatest common factor is 2, and then they each have at least one x. So if I factor that 2x out in front, 4 divided by 2 is 2, and there's one x left. 10 divided by 2 is 5, and the x's cancel. Then I know that my goal is to get those parenthesis parts to match. And so if I look at 10x and 5, the value I'm going to factor out of that second group is 5. And then again, 10 divided by 5 gives me that 2x part, and 25 divided by 5 gives me the 5. And so my final step here is I'm going to group the 2x and the 5 together out in front and say both 2x and 5 are being multiplied by that matching parenthesis part of 2x plus 5. And what I notice when I look at this is that both of my parenthesis parts are identical. It's 2x plus 5 in one and 2x plus 5 in the other, which is a pretty unique pattern. And then if I look even more closely, what I see is that 2x and 5 were the square roots of my first term and my third term in my expression. So what you're seeing here is something called a perfect square trinomial. And essentially this trinomial here is built because this first term is a perfect square, this third term is a perfect square, and this middle term is built by taking the first term square rooted and the third term square rooted, taking those two values of 2x and 5, multiplying them to be 10x, and then we can see two of them here, so we just multiply that by 2. So if we see this pattern where we have a is a perfect squared, c is a perfect square, and the term in the middle is just those two terms square rooted multiplied by 2, if we see that pattern, we can use it to quickly factor. So to kind of give you an idea of what this might look like, let's look at this second example here. So if we take a look here, if we square root this first term, the square root of 16x squared, the square root of 16 is 4, the square root of x squared is x. Then if we look at this third term here, the square root of 49 is 7. So we can see that we have a first term and a third term that are perfect squares. So then what we can check is our middle term. And we check the middle term to see if this pattern will work by taking our first term, which is 4x, multiplying it by this third term square rooted, which is 7. Those multiplied together give me 28x. And so what I'm anticipating is if I were to factor this using the ABC strategy here, I would have two of them. So if I multiply that by 2, I get 56x, which is my middle term. So if you start seeing a values and c values that are perfect squares, there's a really good chance that this strategy is going to work. And what we can then do from here is, while we can still do all of these steps, split the 56 into 28x and 28x and factor it right on out, we also could just jump to this factored form here, because if we're seeing this pattern, we can use it. So instead, we know there's going to be two parentheses. We know that the first two numbers in each parenthesis come from square rooting that first term. So when we square rooted 16x squared, we got 4x. So now we can put the 4x here. Then the second term comes from square rooting the third term. In this case, it's 7. And because this is positive in the middle and we need a positive 56, we would add them together. So you don't have to use this strategy. You could split your middle term if you see a and c are perfect squares and factor it that way instead. That's perfectly fine. But if you're noticing this pattern, you are able to use it to quickly factor. So let's take a look at this next trinomial here. The only difference with this one compared to the last one is that this middle term is now a negative 20x instead of a positive 20x. So we're going to look at how that subtle change might alter our factored form. So we already know that the square root of 4x squared is 2x. And we already know that the square root of 25 is 5. So now what we're going to do is we're going to factor this like we would a normal trinomial. So we start with our a value of 4, our b value of negative 20, and our c value of 25. And then we're going to take a times c, which is still 4 times 25, which is 100. And we're going to multiply to a times c, add to b, which is now negative 20. And so when I think of what two numbers multiply to 100 and add to negative 20, I come up with negative 10 and negative 10 instead. So just a slight change. Instead of positive 10s, these are negative 10s to create a negative 20. So here we have negative 10x minus 10x, and then the rest remains the same. Now if I go through this process, what I notice is greatest common factor here is still 2x. So I factor a 2x out in front and still have 2x first term here. The big difference is negative 10 divided by 2 gives me that negative 5. Then if I factor out a greatest common factor here, I know that I need to match this parenthesis. And in order to do that, I need to factor out a negative 5, because negative 10 divided by negative 5 is going to give me the 2x, and 25 divided by negative 5 is going to give me the minus 5. Then my last step here is I simply group my 2x and my -5 out in front together, and then my matching parenthesis parts become my second parenthesis. And so when I look at this and compare it to the last problem, what I see is that the only difference here is that instead of having plus signs in between the two numbers, I now have a subtraction. And the reason that occurs is because of this middle term. So notice here how it's the same pattern. A is a perfect square, B is a perfect square, and C is created by taking these two numbers and multiplying them, and then multiplying it by 2 because there are 2 in the middle. And so it's really cool to see how that pattern just results in the only change being that there's 2 subtraction signs instead of 2 plus signs. So if we apply this same pattern here, let's take a look. We have the square root of 25x squared. Square root of 25 is 5. Square root of x squared is x. Then we take the square root of 1, which is 1. And so I can now check to see, is this a situation where my pattern might work? And when I take a look at this middle term of -10x, if I take 5x and I multiply it by 1, that gives me 5x. And then if I multiply that by 2, it gives me a positive 10x. And now while I need a negative 10x, what that's telling me is that I'm going to have one of these numbers is always going to be positive and one of them is always going to be negative. So when I put it into my factored form here, I have 5x and 5x, just like I see here. I have 1 and 1, just like I see here. And then because this middle term is negative, we have 2 subtractions. So here in this final example, we're going to look at one more scenario. So here I notice if I square root this first term, the square root of 4x squared is still 2x. If I square root the 25, it's still 5. The only difference here is that there's no middle term and that the 25 is really now a negative 25. So let's kind of see what happens. Now, if you're looking at this saying that you can't factor it, keep in mind that when there's no b term, it's really just a 0x in the middle. That's what's really going on. So this is really 4x squared plus 0x minus 25. And now if we try to use our ABC values to factor this, we have an A value of 4, a B value of 0, and a C value of -25. And if we multiply A times C, we end up with -100 this time, which is a slight change. And then we have to add to B, which is 0. And if we think about it, two numbers that multiply to -100 but add to 0 are -10 and 10. We have one positive, one negative, which accounts for them adding to 0, but then multiplying to be a negative. So if we rewrite this as 4x squared minus 10x plus 10x minus 25, and we start to factor by finding our greatest common factors, so this would still be a 2x, so we have 2x, and then it becomes 2x minus 5. Here, we need to factor out a positive 5, and we get 2x minus 5. And then if we group together out in front, we find 2x plus 5 in the first parenthesis, and then these two match together to be 2x minus 5 in the second parenthesis. And again, what we're noticing is that with the 4x squared and the 25 for A and C, we still end up with 2x and 2x, 5 and 5. The big difference here is that we have one positive and one negative. And the reason that's occurring is because of this 0 in the middle. We know that these 10s appear twice, and if we want them to equal 0, one has to be negative and one has to be positive. And the way for that to happen is to have one positive and one negative within our factored form. Now, the other reason this needs to occur is in order to produce this -25. The -25 occurs by multiplying these two final numbers together, and 5 as a positive times 5 times a negative would give us that -25. Now, to show you this pattern in action a little bit more quickly, if we square root 9x squared here, we're going to get 3x. If we square root 100, we get 10. Because I notice I have a b term of 0x in the middle, that tells me I'm going to have one positive and one negative. So if I jump to my factored form here, we have 3x plus 10 and 3x minus 10. One of each, so that when I multiply things out or when I if I were to multiply things out and factor the longer way, I would have two terms in the middle that cancel each other out. So to quickly summarize what we've seen so far, if we have an a and a c value that are perfect squares, we can use the trick that we covered on the past 3 slides. So you know that as you factor these, they're going to end up with 2 parentheses times each other. So they're each going to end up the same way. And what you saw happen on each is that you can square root your a value, whatever that might be. So here in this case, the front half of your parenthesis is the square root of a with its variables, whatever that might be. And that was the same thing throughout. The first part of the parenthesis was always the square root of a with its variables. And then the second part of that parenthesis was always the square root of c with its variables if it has any. The only difference here that we found as we solved all of these was the signs that go inside of your parentheses. If you have a middle term that is positive or a middle term that is being added in between a and c, your 2 parentheses are going to contain 2 plus signs. If you have a middle term that is negative, your parentheses are going to simply have 2 subtraction symbols inside of them. And if you have a middle term that is equal to 0, you are going to have 1 of each. So that's really the only difference. If you see perfect squares for a and c, you can use this shortcut by square rooting each and putting them right into your parentheses, and then you just look at that middle term to determine do you have 2 positive symbols, 2 negative symbols, or 1 of each. So let's try to use these perfect square patterns to help us factor these 3 expressions we see on the screen. So if we start, we're going to square root the 81x squared to double check it's a perfect square, and I find 9x. We square root 49, and we get 7. And because of that, we can start to make an educated guess that this is a perfect square trinomial. And we know the 9x goes into the first 2 spots in the parentheses, and the 7 goes into the second. Now from here, we just have to decide what this middle term is telling us. And because we have this middle term here as a negative number, we know there's going to be 2 negative numbers. The reason that's the case is because we're going to have 9x times a negative 7, which gives us negative 63x. And then there are 2 of them, so we would multiply that by 2 to get that 126 to be negative. Now if we take a look at the second one here, we square root 25y squared. That is 5y. We square root the 9, which is 3. So that tells me that I have 5y in the front of my 2 parentheses. I have 3 in the back, and then I have to decide what's going on in the middle here. And because I have a middle term that is positive, these will both be positive, so that if I were to multiply that out, the 5y times the 3 would give me 15y, and I would have 2 positives of those to make a 30y. Finally, if I take a look at this third example here, if we square root the 16x squared, we get 4x. If I square root the 1, I get 1. And so as a result, I know that my factored form is going to be 4x and 4x in the front, 1 and 1 in the back. And now what I have to decide is what's going on in the middle. Because there is nothing here, which really means that there's a 0x, it means we're going to have a positive and a negative version of something that cancel out. And because of that, we're going to have 1 positive and 1 negative.